Happy Tuesday. I have 5 after. So let's go ahead and get started. The plan for the day is we're going to start out finishing yeah, well, that's true though. We're going to start out finishing what we did at the beginning, at the end of last class, which was the parallelization of the ball and stick ring network. We got to the point where it successfully ran a simulation, a network simulation. We saw a pretty raster diagram. Should take just a few minutes to go from that to something that runs in parallel. Yeah, so we're gonna finish that off. We're going to do, Ted's going to talk about his exercises on reproducible randomness, and then I think we'll discuss a little bit about, sorry, one second. And then we'll discuss a little bit more about numerical methods and then model DB and model reuse. Does anybody have any questions before we get started? All right. Hearing none, let's go back to where things were last time. Let's see what we have. So you'll remember, and all of this code is available on the general channel. There was a zip file upload 2021-07-15. I will try to remember to link this as in the description on YouTube as well, so that any YouTube watchers can go ahead and grab where we ended up with the code. But we had built ourselves a cell class called ball and stick, and we were able to run it and test it and get an action potential. And let's just go ahead and refresh our memory a little bit on that. So if I were to go ahead and pull up a terminal, there we go. Come on. Maybe I'll pull up a terminal. Apologies, I'm not sure why my computer is running quite so slowly here. But 7:15. So Python, we had ran this thing called ballandstick.py, and what it did was it defined a single cell with 2 parts, a soma and a dendrite, that's the ball and the stick, and it simulated it with a net stem and a net con, recorded it, ran a simulation, printed out the spike times here, and then you'll see it's using Plotly to plot a graph, and it actually did that on the other monitor. But here was our graph. Here was our action potential. And that was one cell living alone, and it did something reasonable. So then we built on this. You may remember from the last video. We built on this, and we built ourselves a ring network. And so what this did is we defined a new class of thing, because maybe we want many of them. And we parameterized it. Our network is going to be on, we could say we're going to do 5 cells or 10 cells. But, all of our basic rule doesn't depend on it, right? It's one cell speaks the other until we run to the end, and then we loop back around. So then we say, okay, well, let's just build it in a parameterized way. And that way, if we have a small model, we can test it locally. And then we can scale it up once we're convinced that the basic behavior seems to be right, to try and do it in a HPC type context. And we had said that there are many ways of defining synapses, and strictly speaking, you don't need to use the parallel context module if you're working class if you're working in serial. But we also commented that if we gave all of our cells identifiers and we worked with the numbers, that it would be really straightforward to go from that serial model to a parallel environment. And I'll show you that today. But so in any case, we construct our cells, we construct our synapses, and we parameterize it such that you take an argument, you pass it in, and you say, this is how big of a network that I want to run. And then it's going to go initialize, run the simulation, and print out a raster diagram. All right, so let's remind ourselves how this works. So we can say Python network.py 5, let's say, and that should give us a ring network of 5 cells. And these are all of their spike times. And and there's a raster diagram. So we see cell 0 fires, then a little bit later cell 1 fires, then 2, then 3, then 4, and then it wraps back around to 0, 1, 2, 3, 4, and so on. We see that the scales, if I were to run this instead of 5, but let's say to 50 cells, then in just a moment, here's all of the spike times, and 0 fires, then cell 1, then cell 2, then blah, 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 all the way up to cell 49, which then causes cell 0 to fire. So we have a parameterized network. And that's basically where we left things last time. Does anybody have any questions on this? Again, the code is available on the general channel of the 2021-07-15 zip file. And again, we'll link it in the YouTube discussion below. Okay, so there are no questions on this model. So then our next task is, can we get this to run in parallel? We've defined everything. All of our connections are based in numbers. And really, it's just a little bit of boilerplate, as we'll see. But I want to step through the process so we see what each piece does. And then we'll see how this all works out. So first things first, if I want to run something in parallel, I'm going to use what's known as, NEURON supports multiple forms of parallelization. But in particular, we're going to work with MPI. So I can say h.neuron_MPI_init. Okay, and that's going to be how I'm going to tell Neuron, by the way, I want you to run this in parallel. It's not really going to have any effect here, but if I want to actually run something in parallel, remember, if I want to do something more than once, I use MPI exec, is going to launch a number of processes in an MPI environment. And if you're using an HPC environment, if you're using Neuroscience Gateway or your local university cluster with Slurm or what have you, PBS, I think, was used to be very common. You can say, hey, look, I want to run with 2 processes, and then I'll just say Python network.py, and then of course I'm going to do, let's say 5 cells. Now we're going to be in for a little bit of a surprise, but let's just see what happens. So this is going to launch 2 copies of this. And you see that it confirms it. It says numprox is 2. Everything looks great. But what's actually happened is it's not done anything to run any faster. And in fact, if I were to go back and look at the output here, well, no, I'm actually surprised. But in any case, it's not done anything to run any faster. Why is that not giving me 2 copies of everything? Just for giggles, I'm going to do a pc.barrier. I thought this would give me 2 copies of everything. There we go. So we actually do have 2 copies of everything. So each process has calculated everything, which doesn't actually save us any time, but it does at least now we have 2 things that are running from one single command line. And so now what we're going to want to do is we're going to want them to work together. And so, by the way, this line that I added just now, this pc.barrier, says that we can't, neither process can finish, neither process can go past the barrier until such time as every process is ready to go past the barrier. So you don't get a weird situation where one of the processes tries to shut down and then the other one goes away. And that was actually the issue that we had just a little bit ago, where it actually did pop up 2 windows, but the one was right on top of the other. And then when the one that was on top closed, that process ended. And so as soon as one process ends, MPI shuts down everything. So you don't want to be in a situation where one process is going in before another. So it's just safe to put this barrier at the end to make sure that everybody's finished before the system shuts down. And that is, you can also do this using MPI for pi. It's a standard MPI technique, has nothing really to do with neuron. All right. So in any case, so now we have two processors are running with one command, but they're not actually collaborating in any way. And they're each doing all of the work. Now, why are they each doing, hold on, my Zoom thing's in the way. Why are they each doing all the work? Well, because we haven't told them to split up the work. So we want to tell them to split up the work. Well, let's look at our ring network. Our ring network identifies which cells that it's responsible for. And it's going to say, well, I'm responsible for all of them. Well, that's not going to save any work. So if I want to have it responsible only for its share, each process responsible for its share, instead of going from 0, 1, 2 up to however many, I need to split that group into different chunks. And there's a number of ways to do this. You might imagine that you want to do the first so many together, then the next so many, then the next so many. There are various reasons why this is actually not that great of an idea. So instead, we'll use what's known as a round robin distribution, wherein basically it's a card dealing algorithm. So process 0 gets 1, gets the first cell, and process 1 gets the next cell, and process 2, and then until everybody gets one cell, and then you loop back around, and then everybody gets the next cell, and then you loop back around, and everybody gets their next cell. And so the way that you do this, from an individual processor's point, is they just start counting at whatever identifier they're at. Okay, sorry. They just started counting. So if I'm processor 0, I'll start counting at 0. And then if there's 5 processes, my next one will be 5, and then after that 10, and then 15. So I will count from whatever my identifier is up to, but not exceeding, however many cells that I want to distribute. And I'll just skip along by how many processors are running, which is pc.nhost. And all of this was explained in last Tuesday's video, but we're trying to actually put this into play. So now processor 0 gets, let's say there's 5 processors, gets cells 0, 1, 2, 0, 5, 10, 15. Processor 1 gets cells 1, 6, 11, and so forth. And so everybody gets their share as if we were doing this card dealing algorithm. Does that make sense? But fundamentally, every cell gets assigned to one and only one processor. So this actually takes us a large part of the way, because this is going to split up our work, but we're going to have a bit of a problem. If I go ahead and just run this, and let's go ahead and run this. MPI exec, remember to run. I'm going to run this with 2 processors. I could use a different number. It doesn't really matter. But if I go and try to run this, it's going to be angry with me, I think. Yeah. Because we haven't actually told it that these processors need to communicate. We're using the traditional continue run infrastructure. So all of the cells, so processor 0 doesn't actually know that it's running in a parallel environment. So in order to run in a parallel environment, we can't use continue run. Continue run is gone. Continue run is only when you're using a serial environment. We instead have to use PC, parallel context object, and then we'll do psolve. And you can think of this as just an analog of continue run. I am going to run the simulation until time 200 milliseconds. But now I'm saying that I want to do it in parallel. You know what? I'm going to go ahead and run this as is. It's going to give us an error, but I want you to see it. So if I go ahead and run this as is, basically the only change that I did from the last time is I changed continue run to psolve. You'll notice that it's like, nope, can't do it. MPI abort, can't do it. And why can't it do it? Because if I'm communicating in parallel, if I'm doing a parallel simulation, then I need to synchronize data, which means I need to know how often I need to synchronize data. Remember, this comes down to the netcon delays. If I have an entire network and the minimum delay is, let's say, 2 milliseconds, then I can go as long as 2 simulated milliseconds without having to synchronize my various processes. So I need to let NEURON figure this all out. And the way that you let NEURON figure this all out is you define, you define a hard limit. You say, no matter what, PC.set max step, no matter what, I don't want the processes getting more than 10 milliseconds apart. And when it does this, what actually happens, if you know anything about MPI, it does what's known as an all-to-all communication. And all of the neurons will talk to each other and they'll all figure out, well, we know we can't go longer than 10 milliseconds, but how far can we go? And they all look and they all say, well, you know what? I've got a delay here of 1 millisecond. Yeah, me too. Everybody has a delay of 1 millisecond in this network. So what's actually going to happen is none of the models will advance by more than 1 millisecond. And so if we don't do a set max step, our simulation will fail immediately because we do have to force them to synchronize. All right, so now though, if we run this, let's see what happens. Now we have to, let's try it again. Let's suppose that instead of doing what we did, we save it first and then we run it. Always a good idea if you make changes to save them before you try to run things. I knew it wasn't saved because there was that big circle instead of the X. Also because it didn't work. So now I see some interesting graphs here, right? I see one graph that's got cell 0, cell 2, and cell 4, and another graph that shows cell 1 and cell 3. Collectively, we've solved the problem, you could argue, right? We have figured out when all of the cells spike. Oh, actually, there's another problem. Let's look at this. Yeah, go ahead.
Just a doubt regarding the last step that you did. You set a hard time for 10 milliseconds, suppose, but in any case, it is scanning out the minimum delay, right? So what was the need for that statement? Because once you give that statement of the PC.solve, then it knows that it has to communicate in parallel while execution. I'm just not, I got confused regarding that when to communicate step, that interval.
Yeah, no, that's a very good question. So a couple of things. First of all, that has to be done. So so there's two questions. First of all, one question is just, why do you have to do that at all? Because there is a minimum. And the other question is, where do we actually do it? So we actually have to do this before the model is initialized. We have to tell it that we are putting an upper bound before the model is initialized. Right now, the way things stand, if you don't do this, the model will not run. And so the answer is, therefore, you do it. I actually agree with you. I think that, so one comment though, this is telling initialize that, by the way, all of this is going to happen in parallel. But I agree, it does seem kind of weird to specify a relatively arbitrary upper bound that's not going to be used. It does give you the ability to keep things from getting too out of sync. If you do want to use a smaller number, that's fine. You use 0.5 milliseconds. That's fine, and then it will cap everything at 0.5 milliseconds since that's smaller than the minimum delay. But I agree with you that it seems a little weird, but right now the answer is just that you have to do it. And I think that's a thing that hopefully maybe we can get rid of in the future.
Okay, thanks.
But at the moment it's required, and just put a big number. 10 is a big number for this case, and you'll be fine. So there's one thing. Yeah, go ahead.
No, thanks.
All right. So there's one other thing that we didn't do here because we sort of rushed through this. But let's look at this. So we've solved this thing in that the cells are firing. But let's look a little closer though, just for kicks. Let's look at this cell. All right, cell 1 here is firing at time 8. Let's look at this cell. Let's look at cell 0. Cell 0 is firing at time 8. Well, that's not good. What happened? Why are they both firing at the same time? Something changed when we went from serial to parallel. Now they're both firing at time 8. And if you're wondering about that, if that could that be right? Let's just say that I go back and I run this without without MPI. If I go back and run this and I look at cell 0 and I look at cell 1, well, clearly cell 1 is firing after cell 0. So here's 0 firing at about 8. Cell 1's firing maybe 11 and a half. So there's something that I didn't do. What's the difference between the two? Why is one process and two process giving different results? And in particular, two processes is having both cell 0 and cell 1 start at the same time. Any
When you
idea?
parallelized it, you split the cells across multiple processors, but you didn't do anything to synchronize the data collection or the initialization.
Well, yeah, and what's getting us here specifically is the initialization. So let's look at that. You'll notice that every time I'm throwing it in to the 0 cell. That doesn't mean the cell with 0 GID. I'm literally throwing it into the first cell that I know about. And if I'm on processor 0, that's cell 0. Cool, that's right. If I'm on processor 1 now, that's cell 1, which is not right because I only want to give one input to this network. And so the way that we do this, we want to target this. I mean, so we could, one option would be to literally, and perhaps this is the most robust option, would be to literally check all of your cells and see if they're whichever ones you want to target and give that stimulus, that cell stimulus. But in particular, we would know that it only should go into one place, and it's only going into the 0 cell is what we're trying to do. So we could, I'm just thinking, you know what? Now I really actually like that other idea. Let's just say, it's a little bit of overhead, but let's just say for cell and net.cells, if cell.gid is 0, because that's what I want to do. I want to go into that cell, the cell with GID 0. And only one of those cells is going to have that. And that way I don't have to think about what processor is doing is. There are ways of avoiding this, but I don't have to think about what processor is doing it. But the only input, definitely unambiguously, is going into the cell with GID 0. Does that make sense? I'm finding exactly the cell that I want to target. I'm not using an index. I'm just literally asking for the identifier. And if you want to go back and try to speed this up and be clever, you can do that. But anytime that you try to speed things up and be clever, it's always good to have a really simple, obviously correct solution that you can validate gives the same answers. So now let's look at this. And now, nope, that's the serial. Well, that's fine. Okay, serial still works. 0 fires before 1. That's nice. Let's try it with two processes. And again, it's running with 2 because of that -n2. So now if I look at this, and I look at the time of cell 1, cell 1, sure enough, is firing about 11 and a half, and cell 0 is firing as a little after 8. So the times are what we expect, but obviously it's a little ugly that the different processes are doing different amounts of work. The different processes are splitting the graph into 2 pieces. Like, this is what processor 0 found. This is what processor 1 found. Cool, I don't care. I just want to see the results. I shouldn't care, as the end user, how many pieces this is all broken into. So what I'll do instead is I need to get everybody to coordinate and agree that one of the processors and only one is going to make the graph, and they're going to have all the data. And the way we do this is to use an MPI communication. And so if you're using the NEURON interface to API, it's going to be, for PC as our parallel context object, it's going to be pc.pi_all-to-all. And what that does is it lets us send a message from each processor to every other processor. And they can be a different message if we want. So what we'll do, and this is kind of formulaic, so I won't belabor the point too much. Right. So then I'm going to go ahead and I'm going to gather up, well, what is my process worth of data? Right. So I've been printing this out, right? You'll see, hey, look, cell 1 and 3 get printed out together, their spike times, and then cells 0, 2, and 4 get printed out together, their spike times. Well, let's go ahead and actually store this in a nice dictionary, let's say. It's just a data structures that we can work with this. And so we'll call this, we're already printing this out, so we'll call this my data. Whatever process I am, I'm going to have some things that I know about. What do I know about? Well, these are the things that I know about, this very stuff that I'm printing out. So I'm going to say, I know that a cell with a given GID spikes at a certain time. When does it spike? It spikes at its spike times. Duh, right? So this is what I know. All right. And then what I want is to know everything. Okay, so if I want to know everything, what I can do, and actually I'm going to do this even simpler than I did it in the solutions that I posted the other day. But here's what I know. I know my data. And so what you send for pi all to all is it needs to be a list of information that goes to every processor. So process 0 will get whatever, we'll get a list of items, and it'll be whatever 0 sent to itself, whatever 1 sent to 0, whatever 2 sent to 0, blah, 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 up to n-1, right? So every processor needs to know about everything. And that's a lot. And I could try to be clever and only send information directly targeted to one particular processor. But you know what? For the sake of this example, just to make it a little bit shorter, but you can see a more efficient solution in the solutions that I posted on Thursday. I'm just going to send a list that just repeats itself. So if I take a list and I multiply it by 4, let's say, I'll get 4 copies of that list. So just to show you in regular Python here, if I have a list that goes 1, 2, 3, and I multiply it by 4, it goes 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I get 4 copies in one list. So now I'm going to send every processor all of the information. There are more efficient ways to do this, but this is the shortest. Every processor is going to learn everything that I know. And then what I'm going to do here, just to show you what this looks like, is I'm going to print out the data that I get. And then, you know what, I'm just going to stop. And so we can stop import sys.exit. We'll stop everything. It's a little brutal, but we can stop everything. So I'm just going to run this, and I'm going to see what it prints out. What do I actually get? So I run this, blah, blah, blah. And I get a list. Let me copy and paste this into a new document here. I get a list that is multiple dictionaries. One dictionary from processor 0, whatever it calculated. It found that cell 0 fired at time 8.25, 24.35, 45, 41.5, etc. Cell 2 fired at 14.57, 31. And then the second thing I get in my list is whatever the other processor calculated. But I could have just as easily run this as with, I ran it with 1, I ran it with 2. I could run this with 64 if I had 64 processors. So what I'll do, so what I have is I have a list of dictionaries. The keys for the dictionary are the cell IDs, the values of the spike times. Okay, so now that I've seen what this looks like, what I had here when I actually made this was just for one network's worth of stuff, but I'm actually looping over everything. So what I'll do is I'll just say for data set in data, right? I sent in all the data, but it actually is, it's the data set that I got from processor 0, the data set that I got from processor 1, and so forth. So I'll just loop over each data set. And then within each data set, I have a dictionary. And that dictionary, we said, consists of keys that are GIDs and values that are spike times. All right. And that was within our data sets items. That's the keys in the dictionary. And then I'll just modify this. It's no longer the cells spike times. It's just straight up the spike times. It's just the GIDs. And voila. So now, if we're lucky, we've gathered all the data. We saw that data knows everything about every process, because the way we did it, knows everything about every other process, all the spike times. We'll just loop through each process's worth of information. We'll use this to make a plot. And yes, sir, there was a question? Maybe not. Okay. So let's save this, let's rerun this, and there's one more step after this before we declare victory. Well, maybe two more steps. So let's go ahead, we'll run this. Hey, everything's on one graph, that's cool. Oh, look, and there's a second one. But it's the same information. It's gonna get, we should check that we get the same results that we got when there was only one processor. So that's good. But there's two copies, one from each processor, and I really don't want two copies. I just want one copy of everything. And so the way we do this is we have to pick a processor that's going to be responsible for displaying it. And there's a number of ways that you could do this, but here's the thing. You know, it could be processor 0, it could be processor 1, it could be processor 37 if there's processor 37. But you know what? You're always guaranteed that there's a 0. Even if you're running with one processor, there's a processor 0. So what we'll do is we'll just have 0, because that's the only one that I can count on exists. So 0, I'm asking you to make the graph. 0 and only 0 will make the graph. And so if we do this and we run this, and then now we should end up with exactly one graph. Yay. So we have the right number of stuff. We use two processors to do it. We know that we use two processors because of the way we did it. But it would be nice to see if this ran faster. Did we do anything any faster than if we hadn't done it this way? So what we can do, just for kicks to test this, and this will be our last thing, we'll just import time. The time module is responsible for keeping track of the passage of time. And so let's just say, well, how long does the actual simulation go? So let's just say I'll start at a certain time. So that's the time.perf counter. There's a number of things that you could look at. Perf counter is a high resolution timer. So it's going to be, it's the seconds, I think, since the process launched. So we'll just measure the time that we started. We finished just, well, you know what, let's wait till we have all the data. So we have all the data here. So elapsed time is however many seconds it is since the process started. So that's time.perf counter minus whenever we started. And we'll let processor 0 tell us how long it did. So print this took elapsed time seconds. And am I printing out anything else? I'm printing that out. I'm bored with printing it. So there we go. So does it run any faster in parallel than it did at the beginning? Because that's kind of the point, right? Let's find out. If I run this with two processors, well, let's start out. I'll run this with one processor. This doesn't quite, we do have some overhead of parallelization, so you should actually check with your serial version. But in any case, when I ran it with one processor, the actual compute time took 0.06 seconds. Cool. What if I run it with two processors? Let's find out. If I run it with two processors, the actual compute time, oh, it's going to make me clear the graph first. We went from 0.06 to 0.16 seconds. Not exactly a win. Why? Because there's some MPI overhead. So what the issue that we're running into is our problem is just too small. So let's suppose that instead we can't, the overhead costs more than the actual simulation. So let's suppose that instead it wasn't one process or one cell or 5 cells, it was 500 cells. If there's 500 cells, it's going to do it, and based on the last one, I'd expect it to take about 6 seconds. This is a very long 6 seconds. There we go. And we didn't run it long enough to actually even get out to 500 cells, so not everybody fired, but that's okay. Okay, it took 8 seconds. Now let's see if I run this with 2 processors. Does it go any faster? And we wait, and it's set up. And we're waiting. And there it is. And it felt faster, was it? Sure enough, this was at 4.944. So even here, we're not getting a linear speed up. You'd expect if it took 8.12 that maybe this happens at 4.06. We didn't quite get that. We did a bigger and bigger problem where the cells took more time. Then the MPI overhead would be less and less. And we'd see a better benefit. But we can speed this up. There's nothing sacred about the 2 processor. So let's say that we ran it with 4. And any moment now. Yeah, cool. How long did that take? So that took 3.1. So we did continue to see a speed up, but it wasn't as dramatic as you might have thought. So again, if the cells are bigger, if the cells are more complicated, remember these cells only have 2 sections, then we'd expect to see a bigger speed up. If our network is bigger, we expect to see a bigger speed up. But if our problem is too small, throwing more processors at it is not actually going to be a solution. Does that all make sense?
Yeah, if your problem is too small, you don't actually have a problem to need a solution.
Fair enough. What you should check, one other thing that I would suggest that you check when you're doing all of this is to, we checked that 1 and 2 were the same. Usually, and it's been my experience that when you think about parallelization, it's always good to go from, there's 3 sort of phases, right? There's doing something once, there's doing something twice, and then there's doing something many times. So you might want to check on your computer as 1, 2, and 4 give the same results, not just 1 and 2. But usually, I think if you manage to get 1, 2, and 4 to agree, you're probably good. I can think of exceptions, but anybody have any other questions? So I talked an awful lot. Yes, sir. But there's not that much that we did today.
I really like this. One quick question though. Suppose there is a gap junction, then at what interval the communication takes place? Because
if there's gap junctions, it's communicating at every time step.
Okay, yeah.
Because it has to. There's not that. Yeah.
Yeah, precisely, madam. Thanks.
The same thing is true, incidentally, if there's extracellular diffusion for the same reason, because it's anything where there's continuous communication, then everything communicates continuously.
And depending on the size of your model, you may find that working with multiple threads might give you better speed up than MPI. So.
And I'll throw out one other thing. As far as continuous communication goes, there are ways of being clever if there's only a subset of your cell, just because you're using the parallel context infrastructure to do the parallelization. If there's only a small subset of your cells that are gap, if there's only 2 cells that are gap junction connection, just throw them in the same processor and then don't tell parallel context about it, because then they'll be just fine, happily talking to each other. And only the spike events need to be propagated using parallel context.
Yeah, that is actually a good strategy, especially if you're dealing with a network that has a large number of inhibitory interneurons. Typically, inhibitory interneurons can be represented by a very few compartments in very few sections. And so they're very tiny compared to pyramidal cells. And it's the inhibitory interneurons that in some parts of the brain tend to be connected by gap junctions into a bit of a subnet of their own. So see if you can't just put them all on one processor. And that way you may be able to completely dodge the issue of per time step communication.
And just to reiterate one of the things that came up in the chat, F-advanced will not work in a parallel setting. Again, because it's really geared towards, it doesn't make sense, because it's really geared towards advancing one time step. And the whole point of this parallel infrastructure is that we can go large lengths before we have to communicate. And it just will, if you use F-advanced, there will be no communication events, and it will not work.
Okay, thank you.
All right, so that's everything that I wanted to say on parallelization. Again, so we've now spread this over, if you're coming into this video, this has now been spread out over 3 videos starting last Tuesday, where we had the didactic material, and then where we started this effort of building this network last Thursday. So with that, if there's no other questions, there was a reproducible randomness exercise from last class.
Okay, I think maybe you're seeing my screen.
Yes.
Okay, that's terrific. Yeah, there was a reproducible randomness exercise, and the question was how to make that that network that I built deal with randomness in a principled way. So as you may recall, well, you may not recall. So let me just take a peek back at that code. So we had a network with just really one cell and a lot of afferent activity, and the interspike intervals of that afferent activity were occurring at an average of 1 per millisecond, and there was going to be a whole bunch of them. But all of these, if I don't do anything else here, are going to be drawing from Neuron's old relatively low quality pseudo-random sequence generator, good enough to fool people who haven't put the data to statistical analyses to show, to try to reveal unanticipated correlations. But you're drawing all random numbers from the same stream, and if you had any other random task, any other task that required a random number, and you drew a sample from whatever distribution it would be, that would advance the pseudo-random sequence generator, and it would change the timing of all subsequent spike events generated by your netcon. And if you added a new netcon and it had some randomness of its own, that would mess up all the spike times as well. So you would find that anything you did that imposed the need for an additional random number to be generated would totally change simulation results numerically. So you wouldn't really know, it would be very hard to tease out what is the actual effect of, say you're doing an experiment where you have a cell barraged with quasi-realistic random background activity, just so it's got a fluctuating membrane potential, and you wanted to know how those fluctuations of membrane potential affected, say, the detectability of a excitatory input that was close to but not quite at threshold. And if you are running then that with irreproducible randomness, you're going to have a hard time regenerating those results to show anybody how you got your data. And if you change your model slightly, say by changing some other parameter in the model by drawing from the pseudo-random sequence, you change all your background noise. And then when you went to see if your sub-threshold EPSP was detected, it might not be, or it might be if it hadn't been before. So what we're trying to do here is we're trying to get around this problem by taking advantage of random 1, 2, 3. And if we do that, we have a couple of things to be concerned about. This is basically the same code up to a point. And I'm going to just highlight the points that are different. Actually, why don't I? Well, no. I won't run diff. Oh, I will run diff. Okay. So this is the output of diff. And the first thing it detects, clever software that it is that I've changed the header slightly. It also notices that I have different number of runs. Wonderful. It also notices the first really substantive change. And that is, I create an instance of random that draws its values from the random 1, 2, 3 generator. And I tell my presynaptic spike source, which is a netstim, to use the numbers generated by this pseudo-random generator, okay? And I'm almost home. I've almost taken care of what I need to do. What I need to do, though, further, is to add a new routine. Rather than getting rid of my old batch procedure, which launched a bunch of runs one after another and collected the spike counts, I decided I would create a new batch procedure that would be designed to produce a reproducible set of runs. So I figure I'm going to be executing n runs. The first run is going to, I'll call it run 0. The last one, I'll call it run n-1. And for each run, I am going to take advantage of random 1, 2, 3's indices to control which sequence I get. So in fact, I'm going to use its first index, ID 1, and I'm going to assign the run number to ID 1. So each run is going to use random 1, 2, 3 with a different value of ID 1, and that value is going to come from which run is it? Furthermore, I'm going to be really fastidious, and I'm going to make sure that I start each run with the pseudo-random generator at the beginning of the sequence. Remember that there is a sequence. A pseudo-random generator produces a sequence of numbers. Okay, when it starts out, if you don't tell it otherwise, it starts out with the first one, which is usually in civilized programming languages, it has the index of 0. Okay, but after you've picked several times from that pseudo-random sequence, there's a counter that advances every time you pick, or, well, in our case, it advances every time you pick. And so if we've already done a run, our counter may have gotten to, say, the 100th sample from a particular pseudo-random sequence. I want to make absolutely sure that when I change index 1 and I'm ready to start the next run, I want to make sure that that counter is reset to 0. So I'm not starting out at the 101st sample with index 1 at its new value. Okay, because I don't want anything to hang over from the end of one run to the next. I don't want there to be any of these dependencies that might trip me up if I try to do things, if I try to, do something reproducible. All right, so that's what I'm doing here. My rep batch procedure starts out, of course, by declaring that counts is a list. And then it iterates over, 0 to n minus 1. And before it even launches a simulation, it sets it sets the ID 1 of random 123, random 123's first index, to a value that is identical to which run we're doing. And then it sets the sequence to 0 so that we're starting to pick from the very first of that sequence. All right, and at the end, we append our counts. Okay, so we call one run and we append the counts returned by one run to our counts list, and then we return counts. And that's how we do it. So that is the total solution. And then when I actually call this, I'll call nspikes equals rep batch parens n runs. So that's the whole solution start to finish. All right. Now, I guess that's all I need to say. I think I'll just put this source code available online after we're done, and that will be it. Are there any questions at this point? Everybody's got it. We will see no irreproducible randomness except in crude hacks for prototyping's sake, right? Won't see any published papers with source code.
That's awfully permissive. I don't know about this prototyping business.
I don't know what prototyping.
You said crude hacks and prototyping. I don't know, man.
Well, yeah. Well, again, it's if somebody is paying you real money and you're getting paid by the hour, you put more effort into it, right? On the other hand, if you're working as a lowly tenured faculty at a medical school where your income comes out of the grant money that you raise, and you're not in an endowed chair, and your time isn't worth $500 a minute, well, you're allowed to take some shortcuts so you can go out and smell the roses. Okay, let's go on to the next thing. So let's see here. Some of this, what I'm going to show you now, might fall into the category of, tell me if you've seen this before. Okay. Whoa, this is way too big. At least it didn't eat my entire screen. Okay. So view, get rid of the side pane, and let's spread this out a little bit more. All right. In my previous methods talk, I did talk a little bit about adaptive integration. I just want to make sure to drive home some points about practical usage of adaptive integration. And these are, when are you going to be doing it? Well, the most typical time you're going to be using adaptive integration is when you're dealing, say, with models of a single cell. One reason why you're going to do that, as opposed to using adaptive integration in network models, I think Robert probably mentioned this already, is that if you have a network, you're going to have obviously more than one cell. And if it's a distributed network, there'll be more than one cell on more than one host, probably. And in a network, oftentimes, well, most of the time, cells aren't perfectly synchronized. So some cells are in their interspike intervals and not doing much. Some cells, and in those cases, things are changing slowly, and NEURON can advance those cells, could advance those cells with longer time steps and making less computational overhead. But the problem is, at any given moment, there's probably some cell somewhere that's approaching the threshold for a spike, or sweeping up toward the spike peak, or turning around and starting to repolarize, doing something that requires you to grind things to grind slowly. And if you're using adaptive integration with global time steps, this means that all cells everywhere are going to be forced to use the same small time step that is needed by the one cell that's got the most complicated task at the moment. So this is going to slow your simulation way down. Now, there is a local adaptive integration method, a local variable time step method, but it turns out to be not terribly useful in network models. Also, not because of the problem I just mentioned, but because of other problems. There's just a lot of overhead involved, and it just doesn't really pay off. So fixed time step is what you're using. Fixed time step, fixed integration method. Okay. So what we're talking about here with adaptive integration applies really, again, to when you're working on individual cell models, in which case adaptive integration may be particularly useful for those cases where you're dealing with, say, a system that really has some complicated processes with complicated dynamics, oftentimes ion accumulation, calcium pumps in particular, where even for the sake of stability, you've got to use adaptive integration. Okay? Either that or else use excessively small time steps for the whole simulation. So we're talking about something that in practice is used primarily with models of single cells. And when you're doing that, your initial debugging and development will probably be relatively interactive. If it's not, you're making a lot of extra work for yourself, or you've given up on doing the extra work and you're allowing stuff to escape your notice. But I'm assuming that you're doing due diligence with interactive simulations and really getting to learn the properties of your model cells. And when you have to, you bring up the variable step control with NEURON main menu tools, variable step control. And that brings up this panel that has a checkbox here, which is empty at first. And if you click on that, it tells NEURON to use adaptive integration. Has the same effect as executing this statement. In HOKE or in Python, it would be h.cvode_active1. Okay? So what does that get you? Well, Robert, I think, has already talked about absolute tolerance. This means, what is absolute tolerance? Basically, what's happening at every advance in a simulation that uses adaptive integration, neurons using an integration package that checks for the local error, okay? And checks for the local error and makes sure that no state variable has an error of greater than some value, which is the set by the absolute tolerance. Okay, so here's an example. When you start the adaptive integration tool, you can click on the ATOL scale tool button, and that brings up a couple of panels that tell you a lot of interesting stuff. And the interesting stuff it tells you is, first, you'll see this list of all the state variables that are subject to numerical integration. And you'll see some other information in these other columns. There's basically 4 columns here, 1, 2, 3, 4. And what is the significance of these things? Well, you see, first of all, if there's been any special attention paid to any of these particular state variables. And that special attention is in the form of state-specific tolerance adjustments. So you notice that for membrane potential, nothing has been done. Okay? And what is the tool which is used via Python to do that for you? Well, let's go back to NEURON Python documentation, and let's look at CVODE, and there's absolute tolerance. Okay. And then there's ATOL scale. What does this mean? It only works when called from Hoke. Oh, this is the way to call it from Hoke in Python. Good. And this is a multiplier that scales the error tolerance. So we see here that for voltage, it doesn't do anything special, but for these variables that belong to this calcium diffusion and transport mechanism, for these 3 variables, it applies a scale factor of 10 to the minus 6th, because these variables have, these variables are very close to 0. They're much smaller in magnitude. Well, actually for this one, it's 10 to the minus 6. For these others, these are like the number of molecules on the surface of the membrane that has the pump. And these are on the order of 10 to the minus 15th. Okay, because these numerically are extremely small. And if you're trying to say, well, we're going to try to keep the absolute error of pump CA diff pump smaller than 1, well, that's meaningless, because the variable never gets much bigger than about 10 to the minus 12th or 15th or 14th or something. It always very small. So this is why some variables need special treatment. Well, now, your next question is going to be, well, that's great. How am I going to make this decision? I've got a dozen different mod files. I'm going to have to record all of these different state variables in the course of my simulation and check them out and make sure that the tolerance scale factors are proper. Well, no, you actually don't have to do that, because this tool actually will discover what the ranges are, and then suggest what the scale factor should be. It'll do that for you. You don't have to reinvent the wheel. So just as an example, toy example of that, let's just do something very quick. I'm just going to start something that just uses Hoke. Okay, I'm going to create a soma darn it. So Oak is similar to Python, but you just take the H dot off of the front of it, okay? So create Soma, and I'm going to say Soma insert dot, excuse me, HH, okay? And I'm going to then bring up my variable step control. Let me drag it down here to where you can see it. There's my variable step control. And I'm going to click on the ATOL scale tool button. And there is my panel with the ATOL scales. Okay, and I see that everything starts out with a scale factor of 1, but we know that membrane potential is special. It starts out at -65 for Hodgkin-Huxley, goes all the way up to maybe +40, can go down to -65. That has a huge range of potentials that it can be, but M, H, and N are always between 0 and 1. So we have a suspicion that we're going to have to do something special for those, because the same tolerance that is really very fastidious for membrane potential. I mean, look, for something that ranges from 1 to 100, that's a pretty small fraction. But for something that almost never gets up to the value of 1, that ain't so small a fraction. So what we're going to do is we do an analysis run. Click on the analysis run button. Okay. And whoops, I'm sorry. And you'll see that it doesn't tell us to do anything much. Analysis run, analysis run. Let's click on rescale. We see these values here. These are the initial values of the parameters, and these are kind of the values that they get to in the course of the simulation. If I click on rescale, you'll see that NEURON thinks membrane potential could be handled a little less tightly, and these other variables need to be handled more tightly. Okay? Well, you don't absolutely have to accept the values that this tool gives you, but these are the scale factors that it recommends for this particular model setup. What kind of a model is it? It's just a cell with Hodgkin-Huxley. I didn't include a stimulus of any kind. I didn't include any other ionic channels. I have no other sections in it. So it's working with a very simple use case. And if I look at these values, I see something a little funny. First of all, I see maybe I'm not comfortable relaxing the tolerance for T by that much. So I can select that and divide by 10 and restore that to a value of 1. And then I look down here at M, H, and N, and I see that although these multipliers are set to 0.1, M is set to 0.001. Now, why do you suppose that is? Because at the beginning, M has an initial value which is very tiny. H and N are much bigger. And if you actually look at plots of H and N in the course of a simulation of a spike, you'll see that M does get extremely small at times, but these two never get that small. So you might be comfortable leaving M, H, and N exactly as they are. Okay, and so you can use these numbers with the ATOL scale method that belongs to CDOD, and you can then apply these in your own Python code. Okay, so when you have a cell that includes, say, calcium accumulation mechanisms, absolutely use that tool to check what the tolerances are, what it recommends that you use for your model. Okay, and then go ahead and include, a note to yourself, even save a session file if you like that reproduces, so you can check these scale factors for yourself and put that aside to where you can reach it in the future when somebody asks you to justify it. And then just go ahead and in your Python, in your Python source code or your Hoke if you're using a legacy program in your Hoke, just go ahead and set up these absolute tolerance scales. All right. Okay, so I'm going to close this example. And this panel, this other panel, is what you get when you click on the details, and it'll show you the integrator and method that NEURON has decided to use based upon the equations that are in your model implementation. And at times it's useful to know that and play around with it, but they're very obscure and you probably won't run into a situation where you need to do anything. So why spend any time on it now? All right, the next thing is just wanted to show what happens in the course of a real simulation. Init and run using this interesting model. This is from the Main and Sinofsky model about the effect of cell shape on cell firing patterns. And this was done at a time when people thought that there was serious literature at the time, and for the previous 25, almost 30 years, about what kinds of things distinguish cells that can fire in bursts, or that tend to fire in bursts, spontaneously or in response to synaptic input, as opposed to those cells that tend to fire single spikes. And you'll find, if you read articles, to this day, you'll find people talking about how this ion channel or that ion channel is responsible for this bursting activity, as if this phenotype is dictated by the genotype. And when they say genotype, they basically mean how are the channels spelled. Well, the truth is more complicated than that. It's not just what channels are present, but it's also the shape of the cell. Main and Sinofsky showed that if you have a circumstance in which there is a separation between the part of the cell that has fast ion channels that gate fast, and ion channels that gate slowly, that kind of an architecture with inhomogeneous distribution of ion channels has a tendency to burst. So what they did was they made a series of models that ranged from small, interneurons to pyramidal cells of different sizes, and showed that with the same ion channels in these different models, exactly the same ion channels, just distributed in different ways. In the case of these little interneurons, they were, just uniform. In the case of these cells, they put the fast stuff near the cell body and the slow stuff out in the dendrites. And they found that indeed these cells tended to fire when they had a separation between the slow and fast, anatomical separation between slow and fast channels. They tended to fire in bursts. Even though they're expressing the exact same channels, these smaller cells did not fire in bursts. Okay? All right, so let's take a look at what's actually going on when we run a simulation with, notice the runtime here, 162 milliseconds. Now this is from a few years back when processors were slower. So results today would be faster if you ran this model on your own machine today. Let's take a look at runtime. And when we run a simulation with adaptive integration, and you'll see that the runtime is much smaller. So things can run faster when you use adaptive integration, but that's not the real reason you're doing it. You're doing it for the sake of improved accuracy. You're also doing it for the sake, in some cases, of improved stability. Some models just blow up because of the stiffness of the equations involved, unless time step is extremely small. And then if you run a whole simulation like this with an extremely small time step, you're going to be there all day. Well, the adaptive integrator is smart about changing not only the order of integration, but the time step of integration. So that if we see what's actually going on here, if we plot, this is our simulation we showed on the previous page. Here's membrane potential generated by that simulation. Here we see the log 10 of the time step used. Just to keep things from exploding, a small positive value was added to dt. So we're not ever taking a dt, we're not actually ever dealing with the fact that in some cases, dt might actually be 0. When is it actually going to be 0? Well, we'll talk about that in a minute. But notice the point here, though, is to notice that the adaptive integrator does adjust the time steps, and 0 means 1 millisecond, 1 means 10 milliseconds, -3 means 1 microsecond. And you'll notice right here at a time that corresponds to the very end of the injected current, you notice there's a sudden drop down to a very small value, okay? You'll also notice here, this is the order of integration, which starts out, I think at 0 at time t equals 0, and quickly jumps up to 3, then bounces around between 2 and 3 during these bursts of spikes. And then after the spike, during the interspike interval, stays at integration order of 3. So here, the error from calculated value to calculated value is proportional to dt to the third power. And then as soon as we start to get close to where the cell starts to accelerate, time step drops, and then pretty soon the integration order starts to change again while we're spiking. And then at the very end, we see not only does the time step drop very small precipitously, but also we see the integration order drops. And what's going on here? Actually, it started out at 0 near the beginning, too. The integration order is dropping to 0 because when a parameter changes abruptly, that is the beginning of a new initial value problem as far as the adaptive integration scheme is concerned. The adaptive integration scheme works fine unless you force a parameter to change abruptly. If you force some parameter to change abruptly, if that's going to have any effect on the simulation that's going to be substantive, if it's going to change, say, dvdt, for example, you may need to restart the simulation. It's a reinitialization of the adaptive integrator, in which case the integration order drops to 0 and the time step drops to 0. And then the first time step is with the next time step is extremely small, and then it cautiously takes a longer step, and then a longer step, and then a longer step, and then again is in the full swing of things, okay? So we're going to have to deal with adaptive integration and what you do when you change parameters abruptly. We'll get back to that later. Just as a finer point of illustration here, you want to just see the times at which NEURON calculated solutions. You'll see the log 10 of the time steps, okay? And you'll see the integration order over here, just zooming in on the first spike in this second burst, okay? Very nice illustrated picture, but all the interesting stuff is going on in this figure on the left. Okay, next, let's take a look to see the kind of fastidious calculations that may occur as a consequence of using adaptive integration. Let's look at this model by McIntyre et al. Of propagation in a myelinated axon. They have a very complicated paranodal model specification, and in the course of a simulation, we're going to see a single spike be generated, and then we're going to look at membrane potential as a function of time at a particular location. This is the 10th node of Ranvier. We're in the middle of the 10th node of Ranvier, so that's the first, second, well, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be the one with the index 10, that one right there. Okay? And we're seeing the spike as it passes that node. These are, of course, space plots. These are plots of membrane potential along the length of the axon, and this is the extracellular potential just outside the axon, with 75 millivolts subtracted from it so that we can see it in the same graph. Otherwise, it would be way up above the top of my monitor. Okay, so we're seeing how there are the these complementary changes of potential at these 2 points. That's all well and good. Here's a model view, which I'm not going to talk about anymore. We'll go to the next slide, and let's take again a look at the detailed time course of the rising phase of this action potential. Here it is in this figure. And if we did fixed step integration with 5 microsecond time step, we would see membrane potential at node 10, in the middle of node 10, would do this. Obviously, node 10 is where we're injecting current, starting at t equals 1 millisecond, okay? This is not something that's propagating from some node upstream, as we might have suggested, might have thought by seeing this right here. There's something special about this node, and I think that's because that's where the spike was being initiated by injection of current. Anyway, let's go back to this, and let's see what's happening to membrane potential there. Well, this is with a fixed time step, and you'll see that we're getting this black trace, and it has a few little kinks in it here and there. All right. But if we did adaptive integration, this is what we would see. Notice the curvature in time of the rising phase. Now, I assume that the person who did this tinkered with tolerance to verify that, in fact, all this wiggly stuff is robust, so that if you changed absolute tolerance a bit, that it doesn't change tremendously. This is qualitatively more or less more correct than what we got with fixed time step. Fixed time step is still good enough at the kind of resolution anybody's going to ever look at this figure, probably. But when you zoom in, you can see how fastidiously the adaptive integrator will try to follow the solution. Okay, likewise, this little bit of an overshoot and this little slight wiggle on the way down. Okay, that's not just some kind of a kink in the plot caused by the fact that we don't have tight enough tolerances. Okay, so I'm assuming this is all legitimate. I didn't generate this figure, I'm just reusing it. Okay, let's go on to the next step. Sometimes adaptive integration can get you into trouble. Here's an example, because it's too fastidious. This is a circuit built with a linear circuit builder that emulates what's used to be done, by muscle physiologists 20, 30, 40, 50 years ago. Yes, even that long ago, half a century, for crying out loud. This is a 2-electrode voltage clamp in which the electrodes are separated by space. In the usual 2-electrode clamp that one might say apply to a large cell like a Xenopus oocyte, one would use one electrode for voltage sensing and the other electrode to pass current into the cell. And the reason you do that is because you want the voltage sensing electrode to pick up an accurate reflection of the internal cellular potential that's not contaminated by the fact that you're passing a huge clamp current through that same electrode. Okay? But in this case, we have a situation where you've got a long muscle cell. In this case, we're talking about an axon. It could be a squid giant axon or a barnacle giant axon, where you've got your voltage sensing electrode at one point and your current passing electrode at a separate point along the axon. And so here's a cartoon of our axon seen from the side. You'll notice how these three sections are laid out like this in this zigzaggy way, which makes it easy to identify where they're connected. If you just laid them out in line, you'd have to grope around trying to find where are they connected. So if you were trying to, say, generate a plot of the time course of membrane potential at these 2 points, and you were using the graphical interface to do that, or you were going to put some other kind of instrumentation at these 2 points, like the electrodes that are used in this linear circuit builder's diagram, you would have some trouble making sure that you actually got the points of connection. So you'll lay out the model cell with a zigzag in it, and that means that in the graphical interface, you can easily find where the break is, okay, where the bend is. All right, so much for that nicety about use of linear circuit builder. We may come back to the linear circuit builder in a future presentation. Here is the time course of the control current, or excuse me, the injected current, the clamps current, and this is the command potential. What are we trying to do with this circuit? We are trying to force the potential at this point in the cell to be very close to the potential generated by this voltage source. Okay? We're trying to make the difference between this measured voltage and this command potential be 0. The way we do that is we have a pair of resistors that have identical magnitude. So this is a voltage divider. The potential at this point is halfway between the potential, the command potential, and halfway and the potential here. And so we're looking at essentially the difference between these potentials. And we're amplifying it and inverting it and forcing that back into the cell as a current. Okay, so the gain of this inverting operational amplifier is what's closing our loop. We have a negative feedback circuit. Okay. All right, so we're trying to control the potential at that point, and we see that we actually have controlled it very nicely. Membrane potential jumps up, stays a while for there, that new potential, 10 millivolts, and then jumps back down. Beautiful. The clamp current looks kind of plausible. This is with fixed time step integration. We see a capacitive transient initially that collapses, and then we see what looks like a development of an inward current, probably carried by sodium, then the development of an outward current as potassium channels open, and then at the end we see a capacitive transient and a return to rest. And we see the initial membrane potential, which is uniform at rest, and we see at 1.5 milliseconds, we see that we've got the potential, at t equals 1.5 milliseconds, we see that the potential at this location, axon 1, 0, this is the 0 end of axon 1, right there, the potential at that point is indeed at 10 millivolts at t equals 1.5 milliseconds. But membrane potential along the entire length of the cell is flipping all around, isn't it? And we see a millisecond and a half later, t equals 3 milliseconds, we've still got really good control of the membrane potential at this point, but membrane potential over the rest of the cell is zipping around all over the place, bouncing up and down, okay? But we have controlled the potential at our clamp point. Now, why this is useful is a different story. You have to read the literature to find out why these people did these things. It looks a little weird to me, probably to you. But this is done with fixed time step integration. What happens if we try to use adaptive integration? Well, with adaptive integration, if we took this capacitor out, we would have oscillations that would completely destroy this figure. Why would we have oscillations that completely destroy this figure? Well, you notice they're extremely fast, okay? They are on the order of 10 to 20 microseconds in duration. And it is an unstable situation here, a very unstable situation because of the spatial separation between these 2 points. And really, we can't really achieve superb control at very high frequencies of the potential there without getting into oscillations And then that even destroys the time course of membrane potential. It does settle down with time, but it's really not very stable looking. And even this oscillation is being held down by the fact that we've introduced a stray capacitance. Well, what the problem is that our feedback amplifier has infinite gain bandwidth product. In other words, these op amps in the linear circuit builder don't know anything about upper limit of frequency. So as fast as you're sampling time, hey, they follow instantly. Okay. So, and whatever gain it has, if the bandwidth is really, really wide, I mean, you have way too big a gain bandwidth product. In a real situation, you have always amplifiers have maximum limits on the rate of slew of their output potential, the speed with which their output voltage can change. And also, there's a limit on how fast a signal they can follow, period, even if you stay within the slew rate. Okay, so, and this is imposed by built-in capacitances and inductances in the integrated circuit or whatever other circuitry you're using, and there's always stray capacitance. And so by attaching this little tiny capacitor between the inverting input and the output, we stabilize the bit. This is reminiscent. Some of you may have been engaged in ham radio. That used to be technology that was very fascinating before the advent of computers. Some people still are. And they would use what they call gimmick capacitors, which basically be a pair of twisted wires with insulation around them. And they just 1 or 2 turns, just get a few picofarads of capacitance for the sake of stability or coupling when you needed a very small amount of coupling. Well, normally you just get, there is normally stray capacitance everywhere on circuit boards, everything, okay? And in the physical world, there would be limitations on bandwidth that would not lead to these oscillations. If we got rid of this capacitor, this would produce absolutely a destroyed output. Okay, so there's an example where adaptive integration can be too fastidious because, again, it can choose ridiculously small delta t's. Now you can specify some limits to that, I think, but just the same, you'd rather not have to be tinkering with the details of adaptive integrators. And you just have to realize that there'll be occasions when things aren't working right, and it may be because it's being too fastidious and you have to do something to tamp it down. All right, what next? We've talked about the fact that adaptive integration is intended for the solution of differential equations. And there's times in the past when, for the sake of efficiency, people would use this analytical approach to implementing channel gating. And the idea of this analytical approach was that for a reasonable small time step, you can treat the gates as being in a particular stage of openness or closeness with a constant value over the time step. And if you do that, what you can do then is you can advance the solution from one time point to the next by using the analytical solution for the gating state. So if we see here, we have a state where there's a time constant and a variable, a rate, excuse me, a gating variable called state here. That actually should be a lowercase o, not an uppercase o. That this state gets updated by adding some constant times the difference between the steady state value for the state and its previous value. So if you think about that, basically you're starting out with at a particular point in time, You know what the value of the O state is. You know that if gating remains constant over the next millisecond or so, you can then say calculate the slope at your time that you're at, and then determine by how much, well, as you don't calculate the slope, you calculate how much decrement it's going to suffer over that millisecond by applying the analytical solution. If it's a first order decay, we know that it decreases by this amount relatively, 1 minus e to the minus dt over tau. The smaller dt is relative to tau, the less the decrement. Okay, so we calculate the value for the decrement over the time interval dt, and then that's what we multiply times the difference between the steady state value of the state and the current value, and we add that to the state, and that gives us our new value. Very fast, doesn't require inverting a matrix. Very nice, and you get this, by the way, with NEURON with fixed step integration. When you're using the CNEXP method, this is essentially the code that NEURON is using internally. You don't see this, but that's basically what NEURON is doing internally with fixed step integration. Adaptive integration doesn't like mechanisms that are specified like this. It doesn't work properly with them. Instead, you need to make sure that all of your dynamics are specified either by kinetic schemes or differential equations. And this is an implementation of exactly the same mechanism, including the misspelling of the state variable. Should be a lowercase o. It's the same mechanism implemented in a form that CVODE, that the adaptive integrator would be happy with. You notice it has a derivative block, not a procedure block. You notice we actually see the ODE, not this analytical solution thing here. And you'll notice that procedure rate doesn't bother to calculate this factor. It just calculates the time constant and the steady state value and makes them available for the derivative block. Okay, and as long as your mechanisms are all specified with ODEs or kinetic schemes, then NEURON's adaptive integrator will be happy with them. If they're not, you'll have to translate them. You have to revise them. Not too many of those are floating around anymore, but if you run into some really old legacy code, and you might, that's what you'll have to do. Okay. Now about abrupt parameter changes. What do we do about things like this? In the bad old days, before NEURON had an event delivery system and could deal with events, there had to be a way of signaling to NEURON's numerical internal machinery when a parameter would change. So, for example, if we wanted to have a current that would follow a function of time once t was greater than some value called delay, we would have to signal that by including an @time statement somewhere in the N-model source code. Okay, this is the breakpoint block for a mechanism that would work with fixed step integration, and it would not work with adaptive integration because adaptive integrator would completely miss this conditional statement. Okay, and if it didn't miss it, it would have to try to hunt around to find out the point at which this jump of the value of I did happen, and that would waste a lot of time in your simulation. So you don't ever want to really do this, and you certainly don't want to ever have to use @time anymore, although you'll see it in some of NEURON's source code that it used for some of the mechanisms, like the iClamp used to use @time. I don't know if it still does. Okay. Instead, to work with adaptive integration, actually to work with all of NEURON's integration methods, and to ensure that you have better maintainable code, it's better to use a self-event. So here's an example of a mechanism that does exactly what this would do in the bad old days, but it's much easier to develop and maintain. The initial block, which is executed when the mechanism is initialized, sets a Boolean variable, well, it's still a floating point number, which I'm calling on, which represents the state of our current source, to 0, meaning the current source is off. And it sends an event, a self event. Net send is used to send a self event, which will return at time t equals del. And it will have a flag associated with it. Every event has a flag associated with it. And when you have a net receive block, you could test for the value of that flag. By default, the flag is 0. So if you just said net send parens del close parens, the value of flag would have been 0. But we're making sure that this mechanism responds only to events that it generated. So we're associating a flag with a value of 1 with this event. So at t equals 0, it sets on to 0, and it sends an event which will return at t plus del, which basically means del, because t is 0 to start. We'll get an event back which has a flag of 1. Let's look in the breakpoint block. If an event is delivered to this mechanism, what will happen? First thing it does is it checks to see if the current source is on. If the current is on, oh, wait a second, it's not a blank. This is a breakpoint block. This is not a net receive block. At every advance in the simulation, it checks to see if the current source is on. If it's on, then it assigns the value to I that is appropriate for this new time. But if it's off, it sets I to 0. And how does this mechanism respond to the self event that it sent? Well, if a self event, if any event arrives, it checks the flag of that event to see if it's 1. If it's 1, then it was a self event that this mechanism sent to itself, and it knows it needs to toggle the status of the current source on. Okay, so it turns the current on. If the flag was some other value, it wouldn't do anything. So this is end model source code, say part of end model source code for a mechanism that would wait until a particular time before it turned on the current source. All right? And it uses a self event to do that. Okay. So basically what we want to do is we want to be able to control simulation flow control. In the middle of a simulation, we want to be able to force certain things to happen at certain times. In HOK, to make sure that we do some x at time t equals 1, the old way to do it would be to alter the standard run system. I'm not even going to discuss this because I don't want you to do it. Instead, it's better to use events. You use an finalize handler. You create an instance of the finalize handler, and you make it call a procedure that does what you want it to do. Okay? And in this case, this is an finalize handler that at time t, excuse me, what this does is it makes sure that it launches a self event at time t equals 0. The self event will return at t equals 1, t equals t1, and force execution of a procedure called p. Okay, so this is the way that you can make something happen at a time called t1. You create an finalize handler and you make it call a procedure. And there's our procedure and what it will do. Our procedure will force P to be executed at t equals 1. Okay, so this is how you put an event in the event delivery system that comes back at t equals t1 and forces P to happen, whatever P is. And if P changes any parameters or states, you need to do a CVODE reinit. Remember how in our adaptive integration scheme, where we had the Manin and Sinofsky cell, we saw how the order of integration plummeted and at the start of the current pulse and at the end of the current pulse. You basically this was what was going on behind the scenes. Okay. If you want to have something happen conditionally, you want to have, say, when some cell makes a spike, you want something to happen in the middle of your run. The best way to do that is with events. Again, you create a netcon that monitors the variable. Say, here's an example where we want something to happen when V goes above some threshold in a positive going direction. Well, you'll use a netcon to monitor that membrane potential. And we have as its target nil. Okay, nil is basically what you get when you declare, well, I don't know, does NEURON have nil built in? Let's see if it does. NRNGUI. And let's see if it knows about nil. Well, I don't know, maybe it does. But if it doesn't, it's easy enough to do it. Object ref nil. And I can say print nil. It's a null object.
Do you think people are seeing what you're typing or not?
Oh, I'm not. They can't see it. Okay, so here we go. Starting NEURON, and then I say print nil. There is no nil. So if I say objref nil, then I type print nil, and it says null object. So now we have something called nil. It's the null object. Okay. So the way we get something to happen then conditionally is we create a netcon that is going to send events to nil. In other words, it just throws them away. We set the threshold that we want for that netcon, and we're making our netcon, in this case, monitor membrane potential at the middle of our soma. And then we use the netcon method record to call procedure P. What's going to happen is in the course of a simulation, every time membrane potential at that location crosses 10 in a positive going direction, it will call this procedure P. It will execute that procedure P. And you can do that in Hoke, you can do that in Python. In fact, the next slide shows the Python equivalents of those. Okay. Here we have the one that does something at a particular time. And there's our HCVOD event at times T1, do P. If we have a conditional, we have our netcon that we created that targets none, and it's monitoring membrane potential of the soma. Its threshold is 10, and every time this netcon detects a threshold crossing in the middle of the soma, it will force the execution of whatever is P. So there's our procedure P. And again, if P does anything to any parameter or state, you need to call HCVOD reinit. Okay? People are always asking, how do I change the concentrations at such and such a time? How do I puff on acetylcholine on this particular synaptic mechanism at a particular time? That's how you do it. All right, final slide I'm going to show, final slide player I'm going to show is from an interesting exercise in which we have a model cell, a single compartment model cell, and we have triggered a spike. It has Hodgkin-Huxley mechanism in it. We are injecting a current with a single electrode clamp into the middle of it, and that is enough to trigger a spike. And we record the membrane potential that was elicited, and then we turn around and we use that recorded membrane potential as the command potential for a single electrode clamp. Okay? And we use vector play. The vector class is play method to use those recorded values to force the command potential in a single electrode clamp. And we see that, yes, we can force the membrane potential of our model cell to follow the spike waveform. But if we look at these steps here, I don't know if you can see, but if we look at them, we see here it's starting to look a little jagged. Okay? And it looks like instead of being nice and smooth, we're actually making membrane potential, this is nice and smooth, we're actually making membrane potential follow a series of steps. Why is that? Well, because what we got when we did our vector recording was we got a sequence of membrane potentials that differ from sample to sample. And if we look at those, they actually do look like a sequence of steps. Okay? We really are forcing the membrane potential of our model cell to jump to a new value and then sit there for a fraction of a millisecond, and then jump to a new value and sit there for a fraction of a millisecond. And every one of those jumps is associated with a capacitive transient, because to make membrane potential change abruptly, we got to dump a bunch of charge into the cell. And that's why the clamp current looks so ghastly. It has all these big jumps, and every last one of them is a new brief pulse of current that enters the cell right at the beginning of that new voltage step. Okay? And if I spread these currents, if I spread this axis out so that I can expand, this now from here to here is just 200 microseconds, you can see the clamp current is 0, then we get this big capacitive transient, and now it's a little bit positive, then another big capacitive transient when we force membrane potential to jump, and it's a little more positive, and then another big transient, and then it falls back and it's a little bit more positive. That's each of these different jumps. And we see how big these transients are. They're huge compared to the actual current that we need. We don't really want to do that. We want the command potential, even though it's sampled, the command potential is sampled at fixed time steps, but instead of forcing the membrane to treat that as a sequence of rectangular jumps, what we want to do is have it treat it as linear interpolation from data point to data point. Okay? We want it to treat this as, we can't treat it as a smooth curve because we've sampled at regular intervals, but we can treat it as if there's a straight line from sample to sample, straight line from sample to sample, straight line from sample to sample. And we do that with vector play with interpolation. Let me just go back here. And if we do vector play with interpolation, we get a nice smooth depolarizing ramp, none of those jumps, and a much smoother time course of membrane potential. We get, for the clamp current, we get basically the step current that we had to inject to trigger the clamp. There's a little bit of slop left over. This isn't a perfect reconstruction of the original waveform, so there is a little bit of error. But if we expand this, we see that our pulse, our current pulse, really is the current pulse that was used to trigger the spike in the first place. So we get that with vector play with interpolation. So here we've had a situation where we have a voltage command, which was actually a series of sampled values, and we could have let it go without interpolation, in which case we got horrible artifacts. But if we do instead vector play with interpolation, we get a much nicer looking result. Okay? When will I ever be doing vector play with interpolation? You might be. So it's good to know about this. Are there questions at this point?
Ted, I have a question. I've always assumed that interpolation would be what you'd almost always want. When would you not want interpolation?
I can't imagine when you wouldn't want to interpolate. But generally speaking, you're not doing, you don't often do vector play with recorded values, A. B, the exceptions might be, say, suppose you have some experimentally measured samples of a synaptic current that you've got under voltage clamp, and you want to be able to play that waveform back into a model cell at the same location where you think the synapse was located. And for that, you definitely would still want to do vector play with interpolation. You're absolutely right about that. If in fact you can say that, well, look, this time course of this forcing function is really nicely fit by an analytical function, and I can write that function out, I can just calculate the numerical values on the fly. I can embed that function in an N-model source code and just have N-model create the waveform for me. And we can talk about that in the context of how to implement, say, a zap function and how that can be done. But I think that's a little bit beyond the scope of today's presentation. And that works extremely well, by the way, forcing things, having analytically calculated forcing functions. And that's a very nice trick to be able to use. Okay, I'm done. If there's any time left, questions? Silence.
All right, so if there's no questions, I'll just say that in the interest of time, we'll put off the Model DB and reusable code discussion until Thursday.
Okay. Very good.